Today, we're analyzing the engineered performance of mycelium as a construction material. We'll be focusing on its verified structural, thermal, and environmental characteristics.
So the entire premise here really shifts construction from extraction to cultivation. And that brings up a fundamental question. Can a building material actually be grown to meet precise engineering specifications? Okay, so what is this material? It's a mycelium composite. It's formed by cultivating what are called hyphae, that's the root structure, of a specific fungus, Pleurotus austriatus. This living network grows through and binds together a substrate of agricultural waste, in this case, hemp herds and ryegreen. The formation is a controlled, three-step biological process. It starts with inoculation, where the mycelium culture is introduced to that substrate. Then comes colonization. This is a 14-day period where the hyphae expand, binding the substrate into a solid mass. And finally, densification, where the composite develops its own natural water-repellent outer skin. First up, let's analyze the material's structural performance to really determine where it fits in construction applications. The maximum recorded compressive strength is 1.2 megapascals. Now, this metric is key. It measures the material's ability to resist being crushed under a direct load.
This table lays out the full range of properties that have been verified through standardized testing. You can see the compressive strength varies between 0.7 and 1.2 MPa, with the flexural strength, its ability to resist bending, at 0.4 MPa. Its density is quite low, from 280 to 420 kilograms per cubic meter, but the key analytical point here is the modulus of elasticity, between 120 and 180 megapascals. This indicates a material that is relatively flexible compared to traditional masonry and that has critical implications for its use.
So, these specifications place the material firmly in the non-load-bearing category. Let's be clear, this is not a direct replacement for structural materials like brick or concrete. Its primary application is for things like infill wall systems and insulation, where its low density and moderate compressive strength are actually very suitable. Next, we'll evaluate its performance in two critical areas for any building envelope: thermal resistance and its reaction to fire.
The material's thermal conductivity, known as its lambda value, is 0.042 watts per meter Kelvin. And just remember, a lower lambda value means higher resistance to heat flow, in other words, better insulation. Now, the implication of that number is significant. In a standard 300mm wall assembly, this gives you a U value of 0.14. This performance actually exceeds the UK's 2025 Part L building regulations, which mandate a U value of 0.18 or lower. So this makes it a genuinely high-performance insulator. And what about fire performance? The material achieves a European classification of B-S1D0, according to the standard BS-EN 1350-01-1.
So what does that code actually mean? Well, it breaks down into three key safety metrics. B means it has a very limited contribution to fire. S1 indicates the lowest possible level of smoke production. And D0 means that no flaming droplets or particles are produced, which is critical for preventing fire spread. All right, let's now turn to the material's life cycle to quantify its environmental impact. The embodied carbon of this mycelium composite is calculated at negative 15 kilograms of CO2 equivalent per square meter. That negative value is the critical factor here. It indicates that the material is a net carbon sink. And this chart provides the crucial context. While conventional materials like brick and concrete have these huge positive embodied carbon values, mycelium is carbon negative. What this means is that its biological growth process actually sequesters more atmospheric carbon than is emitted during its production and transport.
This really illustrates the material's fully circular life cycle. You start with an agricultural waste stream. After a growth phase, it serves a 50-plus year life as a building component. Then, at its end of life, it's fully biodegradable and can be composted right there on site, returning nutrients back to the soil. So, to summarize the key performance metrics we've covered, the material offers a compressive strength up to 1.2 megapascals, a superior insulation U value of 0.14, a very high fire safety rating of B/S1/D0, and a carbon negative profile of minus 15 kilograms of CO2 equivalent.
So, the key takeaway is this. While the biological principles and performance are proven, the primary challenge is one of engineering precision. Scaling up production to achieve the consistent dimensional tolerances and mechanical properties required for widespread adoption, that remains the next critical step for this technology. Today, we're diving into a pretty radical vision for the UK housing sector. We're talking about a plan that tries to solve the housing crisis and the climate crisis at the same time, using materials you probably have in your home right now. Okay, let's get into it. So this is the big question, right? It's really at the heart of everything we're looking at today. We're going to break down the data behind this really innovative idea that turns our old plastic waste into high-performance building materials. Let's see if the numbers really stack up. All right, first up, let's look at the core technology itself, because this isn't just about recycling in the way you might think. We're talking about completely re-engineering waste into something, well, something much stronger. And the key to this whole thing is a product called a biosip. So what is a biosip? Well, it's a type of structural insulated panel. The bio part is a little bit of a misnomer because the main ingredient is actually high-density polyethylene, or HDPE, the plastic from milk bottles and detergent containers. The name really points to its role in creating a more sustainable, circular economy. This plastic waste gets melted down and then reformed into these incredibly robust structural panels. Now, this is where it gets really interesting, the performance data. We're not talking about flimsy plastic sheets here. With a compressive strength of 3.2 kilonewtons per square meter and a top-tier A2 fire rating, these panels are engineered to meet and sometimes even beat the UK's really strict building regulations. The data confirms it. This is a serious load-bearing construction material. And this visualizes one of the biggest reasons for this technology: embodied carbon. That's all the greenhouse gas emissions that come from making the material in the first place. The biosip pail, it's sitting at just 28 kilograms of CO2 equivalent. Now, compare that to traditional concrete masonry at 145. That is a massive reduction, over 80%. A huge environmental win before the building is even up and running. So, you've got this innovative material, but how do you actually build with it? Well, these panels are designed for something called Modern Methods of Construction, or MMC. The whole idea is to shift most of the work away from a muddy, chaotic building site and into a controlled factory setting. It's all about precision and efficiency. And the result? Well, because these large interlocking panels are made off-site, you need a lot fewer people on the actual construction site. We're talking a 42% reduction in labor. And that's not just about going faster, it directly tackles the skilled labor shortage that's a huge problem in UK construction. It just makes big projects more doable. It's not just about people, it's about materials too. That factory precision means everything is cut to the exact size needed. So this system slashes on-site construction waste by 65% compared to traditional building where all the cutting and fitting on-site creates a ton of debris. So you've got fewer people on site, you've got less waste. And what does that all add up to? Speed. All these efficiencies mean that homes can be finished up to 30% faster than traditionally built ones. For a country that desperately needs more housing, that is an absolute game changer. Okay, so that's the theory, the data, the potential, but how does this system actually perform in the real world, here in the UK? Let's dig into the data from a couple of pilot projects that have really put this to the test. Our first stop is in Warrington with a big retrofit project by Your Housing Group. Now, interestingly, the focus here wasn't on the actual houses, but on replacing a huge amount of fencing across 120 properties, using a material based on these same recycled plastic principles. And the results? Well, they pretty much speak for themselves. Over a 2-year period, the recycled plastic fencing needed zero maintenance. It was also cheaper to install per meter, and it had a 72% lower carbon footprint than the traditional timber alternative. For a housing association, those savings on cost and labor are absolutely massive. Okay, next up, let's head to a new build social housing project in Quambrin, Wales. Here, the goal was to build entire homes that were not only sustainable, but also hit the absolute highest levels of energy efficiency. And the performance here was, well, it was exceptional. These homes got a Standard Assessment Procedure, or SAP, rating of 92. To put that in perspective, that's the equivalent of the best possible energy performance certificate rating, an A. It just blows the local average of EPCC right out of the water. It's a real testament to the building's thermal performance. And for the people who actually live there, this is where the data really hits home. It translates directly into a 28% reduction in their annual energy bills. In a time of really volatile energy prices, That kind of saving isn't just nice to have, it can be life-changing. Okay, so with these case studies proving the concept, the conversation naturally shifts from if it works to how you scale it up to meet the UK's massive housing targets. This is a really ambitious vision, and it needs a credible industrial plan to back it up. So this slide shows the planned manufacturing ramp-up. We're starting from a current capacity of 12,000 square meters a month. The plan is to quadruple that by 2028, and the end goal by 2030 is to have enough factory capacity to supply materials for the government's ambitious new housing targets. But of course, a shift this big isn't all smooth sailing. There are real challenges. The supply chain for these new materials is still pretty new. You need to train up a whole workforce of certified installers. You've got to overcome public skepticism about building homes out of, well, not bricks. And finally, planning authorities often want to see proof points from established schemes like BREEAM. These are the main hurdles that need to be cleared. So, let's put all this data together. What could the UK's housing landscape actually look like by 2030 if this vision becomes a reality? We're really talking about a fundamental change in how we build homes. Well, projections suggest that by 2030, materials like these biocomposites could make up 22% of all the materials used in new UK homes. That's over a fifth. For what's essentially a brand new material class, that would be an incredibly fast and significant entry into the market. And the impact on a national level, it would be profound. A 41% cut in the housing sector's emissions compared to 2021, a 65% drop in construction waste, and a 42% reduction in long-term maintenance costs for everyone. These aren't small changes, these are transformative numbers.
Ultimately, it all boils down to this. The data suggests this new blueprint isn't about making compromises. It's about achieving all three things at once: superior technical performance, a dramatically lower carbon footprint, and reduced lifetime costs.
And that leaves us with one last question to think about. We've looked at the specs, the real-world performance, the national projections. The data certainly points to a pretty compelling new way to build. The real question is whether this kind of data-driven innovation can be scaled up fast enough to be the key that unlocks both the UK's housing crisis and its climate challenges. Thanks for joining us.
Picture this: a typical UK semi-detached house. Brick exterior, concrete foundation, UPVC windows, cavity wall insulation. Built to last 60 years, costing £180,000 to construct, consuming 12 tons of embodied carbon before a single occupant moves in.
This is the standard template for 28 million UK homes. But beneath this familiar silhouette lies a carbon catastrophe of unprecedented scale. The UK construction sector emits 156 million tons of carbon dioxide annually, equivalent to all domestic aviation and shipping combined. Concrete alone accounts for 8% of national emissions, surpassing the entire aviation industry. Each new home requires 60 cubic meters of ready-mix concrete, generating 12 tons of carbon dioxide before the first brick is laid. Multiply that by 160,000 new homes every year, and concrete becomes Britain's invisible polluter. But carbon is only one pressure point. Regulation is tightening. The Future Homes Standard mandates a 75 to 80% reduction in carbon emissions for new residential buildings. Part L building regulations now demand air tightness below 3 cubic meters per hour per square meter, while U values under 0.18 watts per square meter Kelvin, and a 31% reduction in primary energy use. Traditional construction struggles to comply. Masonry walls require triple glazing, mechanical ventilation heat recovery systems, and increasing material complexity just to meet baseline compliance. Costs rise. Carbon remains embedded. Scale becomes the enemy. This is where the material system breaks, and where a new one begins. Mycelium composites, grown from fungal networks on agricultural waste and recycled plastic structural panels, are no longer experimental. They're BRE tested, regulation compliant, and already deployed in UK pilot housing projects. These materials do not reduce carbon incrementally. They remove it from the equation entirely. Unlike cement kilns burning fossil fuels at 1450 degrees Celsius, mycelium grows at ambient temperature. Unlike virgin plastics, recycled polymer panels operate in a closed-loop system. Construction shifts from extraction to cultivation, from combustion to growth. This is not a design trend, it is a structural correction. The question is no longer whether these materials work. It is how quickly the system can scale.